Hello, welcome to our second lesson, decomposition and synthesis reactions, whatever that is. But we are learning to use mathematics, yes, math, to model. Remember, modeling is to show chemical reactions. Okay? So, what is a chemical reaction? Let's talk about what that is. And what's a chemical equation? That sounds like math. What's a decomposition reaction? And what's a synthesis reaction? Let's take a look at it. So, chemical reactions. The definition is a process or a procedure. Remember, procedures, what we learned about, is that rearranges the molecules of a substance or substances, because a chemical reaction can involve multiple things. Now, the simple version is when a substance reacts to a new situation of some kind, you change something, and it changes the molecular structure. So we see here our water, right? That's connected this way. Something here changes, that would be a chemical reaction. Now, when we did electrolysis in our lab earlier in the unit, the water decomposed into hydrogen and oxygen. That was the kind of chemical reaction that happened. Now, not all reactions or physical changes are chemical reactions. This is a very important difference about what is and isn't a chemical reaction. Some reactions are just pure physics. Boiling water is not a chemical reaction. Neither is freezing water. The water vapor, that gas, it's still water. It's not decomposed into elemental hydrogen and oxygen, which you can tell because if you boil water, you don't get gas that does what happened on our lab. Now, chemical equations. A chemical equation uses chemical formulas. Remember, we did H2O the other day to model a chemical reaction. And these equations, like algebra equations, need to be balanced, right? It's equal to something, and both sides have to match. Okay. These equations will always show the least amount of molecules in the reaction on both sides. Our lab for electrolysis involved trillions, billions and billions and billions, and completely impossible to truly visualize number of molecules of water. But when we do our equations, we just show the least on each side so we know what it looks like, even if it's happening billions and billions of times. So an example here, we have H2O liquid, and this little symbol shows it's reacting that way. It's going from left to right, Hg plus Og. Okay, and this means that liquid water is breaking it into its pieces and forming a hydrogen gas and an oxygen gas. Wait, something seems wrong though here, right? If I look at it, I'm like, wait a second, does this seem right to us? This is the true example. And the reason why this is a true example, because if you look at the top, there's oxygen. There's one oxygen and one oxygen on both sides, so that kind of makes sense. But if you see how there's two hydrogen on the left, but only one on the right, that doesn't make sense, right? Where did that extra hydrogen go? It doesn't just magically disappear. We have to balance our equation. So here where there's two hydrogen, so 2 H2O plus 2 H2 plus 1 O2. That's interesting how there's these pairs, right? There is 4 hydrogen and 2 oxygen on both sides. 2 times 2 is 4 hydrogen. But what's going on? Well, here's some tips. Some elements, like oxygen, they're super clingy. Maybe you have a friend like that. They're super clingy and they don't like to be alone. They come in pairs, O2, oxygen, plus 1 oxygen, in their elemental or pure forms. Another tip on chemical equations, a regular number in front is how many copies of the entire molecule. If it says 2 H2O, there's 2 of them. Easy. The lower number, the baby number, is how many copies of the preceding element. H2O, that little 2 means there's 2 hydrogens. Okay, we see that example here, bolded out. Now, if a reaction is not balanced, sometimes, one or more of the molecules in it need to have more copies. That's usually what's the issue. If you've written it out and it seems to make sense, you're like, wait a second, why is this not balanced? You might need to add some more molecules so that all the numbers work out. Okay, now here's a visual picture of what it looks like, the H2O electrolysis reaction we did. Okay, and this is a decomposition reaction. Decompose means to break down, just like how when food decomposes, bacteria is breaking it into pieces, little tiny pieces that are not the same, and they eat it, right? Decomposition reactions are when one complex molecule, different kinds of atoms, break apart into two or more simpler molecules, right? We might be looking at simple ones right now, but it can be more complicated. And there's our example we've been using for a while about water turning into hydrogen and oxygen gas. Now, this example on the right has two elemental molecules at the end, pure hydrogen, pure oxygen, but it can be compounds as well. Here's an example of a compound breaking down where we have two sodium, oxygen, and hydrogen atoms, right? Breaking up into 2 sodium and an oxygen plus water, H2O, at the end here, okay? Now, our next kind of reaction we're talking about is a synthesis reaction. It's a mirror of decomposition. It's kind of the reverse of it, the flip of it. And it's like Vegeta and Goku here forming Gogeta, where it's the synthesis of two or more molecules combining to form one molecule. Example here is hydrogen plus oxygen turning back into water, is what we saw when you have the hydrogen go pop, right? Now, did you notice? This is an example of a reversible reaction where it can go both ways, okay? Now, just like in decomposition, this synthesis can involve elemental molecules, like we just saw, pure molecules, or compounds. Another example here is carbon monoxide, CO, plus pure oxygen, O2, forms CO2, or carbon dioxide. But this does seem a little wrong, right? Because there's currently 3 oxygens. So this wrong example here, you can see there's 3 oxygen on the left and 2 on the right. So we got to do something different. There's 1 extra oxygen. We're going to increase 1 on the right. So now there's 2 carbon dioxides. But that means you have 4 oxygen on the right and 2 carbon on the right. So we need 1 more carbon and 1 more oxygen on the left. That makes sense to us? So, well, there is a molecule that has carbon and oxygen. So we're going to double that one. Now we have 2 carbons, and then 2 oxygen plus 2 oxygen is 4 oxygen. This side has 4 oxygen as well. 2 times 2, 4.